Let's look at the E2 reaction of substituted cyclohexanes, such as the isomers of 1-bromo 2-methyl cyclohexane that I have here. I've got the trans and the cis-isomer. And I want to remind you that normally when we run an E2 reaction and we have a choice between getting a double bond on a more substituted carbon or a less substituted carbon, we end up expecting to get the more substituted product. And in this particular instance, that means we would expect to get the double bond between these two carbons. It turns out that that's not what happens in this case for the trans substituted compound, but it does happen for the cis substituted compound, and I want to look at why that is. And in order to understand why that is, we need to start by looking at the three-dimensional structure of this molecule. And I can draw the chair form of that, which will look something like this, with my bromine and my methyl groups axial. These two hydrogens are equatorial, and I've color-coded things so that we can keep track of them. I can actually make a 3D model of that, which I've shown over here. So this is my bromine, this is my methyl group, this is my hydrogen on this carbon, and this is my hydrogen on the other carbon. And what I want you to remember is that for this reaction to happen, an E2 reaction requires the leaving group and the hydrogen that gets taken to be anti-periplanar to one another. And that's not the case here. If we look in my three-dimensional model, if I line up these two carbons, you can see that my bromine is here and my hydrogen is here. To be anti-periplanar, the hydrogen would have to be down here. This is almost like a Newman projection between these two carbons. And I can draw a Newman projection of this reaction. It would look something like this, with the bromine and the CH3 anti to one another, this bromine and this hydrogen right next to one another. They're not anti-periplanar. So this hydrogen does not get taken very readily. And there's a really good reason for why that is. If we look at the transition state of this reaction as it's happening, if we're trying to take this hydrogen to put the double bond in the more substituted position, what happens is, as this bond starts to break, a p orbital starts to form. As this leaving group starts to leave, a p orbital starts to form. And what it looks like is something like this, where I can start to see the p orbital starting to form here, the p orbital starting to form here, trying to start to form my pi bond between these two carbons. And remember, for a pi bond to form, the two orbitals, the two p orbitals, need to be parallel to one another. We get side-by-side overlap. These two are definitely not parallel to one another. They're almost perpendicular to one another. So there's no pi, or very little pi bond character in the transition state. So very little stabilization of that transition state. On the other hand, if I look at removing one of the hydrogens from this less substituted position to form the less substituted double bond, what you'll notice is the bromine, my leaving group, and one of the two hydrogens are anti-periplanar to one another. And if we look at the transition state for that reaction, it looks something like this. And you can see the two p orbitals that start forming are parallel to one another. They do overlap side by side very well. I do start forming some of my pi bond during the transition state, which helps stabilize the transition state and gives me some lower energy transition state, so that this is the product that forms more rapidly. And this is my major product. I can do a similar analysis for my cis substituted cyclohexane, which does give me the more substituted alkene product. Again, I'm going to start by looking at my chair structure. In this case, it's the hydrogen that's axial instead of my CH3 group. I can also look at the Newman projection for this structure, and you'll notice that the bromine and the H are anti-periplanar to one another. I can look at my three-dimensional models, and my three-dimensional model of the transition state as it starts to form looks something like this, where you can see my hydrogen and my bromine are anti to one another at periplanar. You can see that the p orbitals that start to form are parallel to one another. and can start to form my new pi bond in the transition state. They can stabilize my transition state, thus helping make this pathway towards the more substituted product a favorable pathway. So I'm not going to get just this product, but this would be the major product in this case.